Rammed earth is a form of unbaked earthen wall construction in which walls are formed by compacting moist subsoil inside temporary formwork. Along with its bedfellows cob and adobe, rammed earth, or peasy construction as it's sometimes known, has been around for a long time. The 1,200-year-old Alhambra in southern Spain is largely built using rammed earth, as are sections of the Great Wall of China. This programme refers to walls built with either sandy gravelly subsoil with 10 to 20% clay or just from rammed chalk with no cement, more of which later. In the UK, there are a scattering of rammed earth schemes, most of them pretty old, like this 5-storey house in Winchester dating from the mid-19th century. But in this age of sustainability and eco-friendliness, rammed earth, which is a BREEAM A+ material, is back on the radar. It has low CO2 emissions, it's recyclable, has a high thermal mass, and it's a natural, breathable product. And it looks nice too. Schemes such as at the Eden Project and at the Centre for Alternative Technology in Wales are two recent examples. Let's start, though, at an undisclosed site in West London where Roland Keeble, who worked on the Eden and WISE schemes, is building a 14-metre-long rammed earth wall for a new eco-centre.
This is an external wall. It's 14 metres long, 2.2 metres high, it's 400 thick. 80% of it is sand and gravel. Normally we would take about 70% of everything that we use is taken from site. And so that might be material that we've dug up on site and it's perfect for use, or material that we've dug up on site and then we've added some sand, or we've added some stones, or we've added some clay. But in this case it's all engineered off-site and brought to site in dumpy bags. It's 20% silt clay from a clay works, and the remainder is an MOT type 1 material. That's 20 millimetres is the largest size, down to sand as the smallest particle size. And that gradation of material is fairly similar to what you'd be thinking about if you were pouring concrete. It's just that we've substituted the binder from chemical cement to clay. So it's a very meaty wall at about 2 tons to the cubic metre. So it's the same kind of density as concrete. It's only that the bindings that hold it together, the clay, is an electrical bond rather than a chemical bond. So from a sustainability point of view, you can knock it down, crush it all up, add some water to it and rebuild it again. And that's something you can't do with concrete.
When cement rather than clay is used as the binder, the structure is referred to as stabilised rammed earth. While stronger and more waterproof than unstabilised rammed earth, these students at the Centre for Alternative Technology in Wales will no doubt learn that in the UK and Europe at least, the absence of cement is one of its strongest selling points.
From my own personal point of view, the point of having cement, not having cement in the walls, is that we're building quite low structures. I mean, these could be 3 or 4 stories quite happily and clay bound. In this case, it's a single story, and the point of using clay as a binder rather than cement is that cement is now 10% of our global carbon dioxide emissions. It's one of the fastest growing emissions that we have. So anything that we can do to reduce those emissions from, take them out of the construction process, the better. Cement is an amazing material. It's a very, very high-tech engineering material. If you're building a road up in the sky, clearly you're not using rammed earth. But if you're building a 2-storey dwelling, then you really shouldn't be using cement. It's a question of resetting our gauge for what is acceptable.
Whether cement is in the mix or not, the construction method is the same.
What we're using is a manhandled concrete system, and the difference between using this for what we're doing and for concrete work is that with concrete work you'd build the whole wall's worth of formwork, and then you'd pour it and then you'd vibrate it, and then you go away and let it set. But we are putting it in layers. The soil, it's a kind of dry mix in layers of 150 mil loose down to 100 mil compacted. Those distances can vary, and it'll give you different surface finish. But in this case, we're doing 150 down to 100, and we'll do that for the first 600 millimeters of formwork, and then we put the next 600 millimeters of formwork on, and then the next, and then the next, until we're finished. And because it's compacted, it's not a liquid like concrete. There's no more pressure at the bottom than there is at the top, and it's compacted on the day, and so we will take the formwork off as soon as we have finished, because nothing will change in the wall until it's dried. It gets harder by drying, and it can't dry inside the box, so you have to take it out. And then of course you get into all of the issues of protection against rain and the other trades on site and all of these kinds of issues.
The compacting process described by Roland is crucial to the success of rammed earth walls. The Wise building in the Centre for Alternative Technology in Wales is a case in point. Dominated by a curved 7-metre tall rammed earth wall which supports the building's roof, is the tallest of its kind in the UK. But during construction, a section collapsed. Project architect Pat Borer explains why.
There was a problem. Part of the wall collapsed as they took the shuttering off, and this is because the contractor basically didn't follow the specs, which asked for 100 mil layers rammed down, as you can see, to 50 mil. So that's the finished layer. It started off that big and went down to that big. And if you do it in too large a layer, then the bottom doesn't compress. Because if you look at each layer, the very top of it is well compressed and the bottom of it is less compressed. So that was the problem. So they had to rebuild part of it. But, disaster, yes, commercially for the contractor, but they could reuse the same material. It's not like concrete, it's just earth. So it was demolished, broken up and done again. And this time they did it extremely well.
As well as correct compaction, moisture content at time of construction is also crucial. And there's a very simple but reliable test used on site.
We're looking for a very dry mix. So the materials come in too dry, we're adding moisture to it as we're working. It means that in a situation like today where it might be a little bit drizzly, we can carry on working, we're just adding slightly less moisture to it. And that is tested with the drop test. And the drop test is just making a ball of material in your hand, pushing it together very tightly and dropping it from your shoulder and seeing how it breaks on the ground. If it falls as a single lump, then it means that there's too much clay or it's too wet, or both. If it atomizes, it means there's not enough clay or there's not enough water, or both. If it breaks into a pattern of 4 or 5 even-sized pieces, then you're at optimum moisture content. Optimum moisture content means that the clay is just wet enough that when it's compacted, it can act as a lubricant to all of the other particles, so they can slide over each other and expel all of the air. And in that way you get the densest matrix of material that you can.
At present, there isn't a British standard for rammed earth. But there is a BRE guide, the result of a 30-month government-funded research project. Led by Pete Walker of Bath University, the project found, among other things, that unstabilised rammed earth walls can have a compressive strength of up to 3.5 newtons per millimetre square, not too dissimilar to a common Victorian house brick. This 2.8 metre tall, 350 millimetre square column buckled after 10.2 tonnes had been applied.
This material is going to crush at about 2 newtons per millimetre squared. We've used chalk material, which is crushing at 0.8, and built 2-storey structures with concrete first floor, masonry domes, green roofs. In that case, the walls just get a little bit thicker. Our normal wall thickness for a structure like this would be 300 millimeters. In this case, we've been it's requested that we do 4 by the architect, 400 millimeters. We'd expect to use a soil anywhere from 0.8 as being probably the lowest, up to 3.5. Stronger than that, and it's probably because it's got lime in it. And we would tend to use lime in a situation of extreme exposure. So that might be at ground level, below a damp-proof course, and so on.
How unstabilised rammed earth walls cope with exposure to the wind and rain in general is a key consideration, as Roland discovered at the Eden Project Visitor Centre, where he and his team built 2 45-metre-long walls.
We said at the time, okay, well, we're going to varnish the outside, and we use sodium silicate, which is it's a non-bound, it's a non-chemical reaction varnish, which we use quite a lot inside to stop dusting, but we used it on the outside, and it was a mistake because it was never maintained, and you don't see a varnish breaking down. If we'd painted it white, then you would know after a year or 2 or whatever it was that you had to repaint it because you could see it starting to break down. But with a varnish you don't see it breaking down. And so what happened was that moisture came in behind and threw off little chunks off the outside face. So from that point I would never varnish an outside face. I would just leave it as it is. If it washes a little bit out and gets a slightly stonier look to it, that will become a very hard weathering surface. In the case of Eden, what we've actually done is worked with a contractor that works with clay plasters. They manufacture and apply clay plasters. We've worked with them to find a colour mix which is acceptable to the client. We have righted a design issue at the base of the wall where there was a shadow gap, which really doesn't work with rammed earth. It's just too fine a detail, and we've actually filled in that shadow gap using the plaster, and those little areas where the little bits have spalled, we've filled with a clay plaster. And then you get a very good fit between clay, and that wall will probably be good for a whole lot longer.
The Eco Centre wall here in West London will be treated, but only on the inside to keep dust down. Outside, the plan is to leave it exposed, the hope being any weathering will add character and depth to it. Watch this space. What about inside? How do earth walls tie in with the rest of the building fabric, and how does earth like being drilled and chased for light switches, sockets and the like?
It's relatively easy to fix things to it because it's pretty strong, so you can use usual frame fixings, expanding bolts, as long as they're not too near the edge. You can do that in a normal way, so the door frame you see there is simply bolted to the wall by expanding bolts.
The way that you fix into rammed earth is pretty similar to, I would liken it to soft brick and lime. Fixings need to go in deeper than they would with concrete, but they're all basically friction or shear type fixings, rawl bolts, chemi anchors. The only chemi anchors we don't use are the broken glass type. The liquid just soaks into the wall before it has a chance to go off. But 2-part epoxy resin, all of those kinds of things we use.
We often put rebates. It's very easy to build in a sort of rebate for a door frame or something like that into the shuttering as you're doing it, as you do with concrete. It's exactly the same.
In this case, the tie-down bolts for the roof we're building in as we go, which we've been asked to do, which is quite unusual. Typically, contractors would ask us to just leave the wall and they will post-fix, drill and post-fix. We know that most of those types of fixings sunk down into the wall, 300 mil will give you something like a ton pull-out. So when you've got a number of those, it's quite sufficient for holding the roof in place. Other types of things like shelves and other types of fixing on the surface, same issue, you're going in a little bit deeper than you would with concrete, but essentially it's the same.
Despite the abundance and ready availability of the suitable subsoil, rammed earth walls are not inexpensive. Most new rammed earth walls also require a sturdy footing or plinth, more often than not made from blockwork or concrete. And of course, just like concrete, they are labour-intensive and require heavy-duty formwork.
You could probably say, to quote, it's reassuringly expensive. When I did some sums on a previous wall, it was about the same price as doing the whole wall in good quality, fair-faced brickwork. So, not ridiculous. Obviously the materials costs are really low, but there's a very high labour content. So it depends. If you're doing it yourself, it's going to be extremely cheap because your labour is so-called free. But if you're using contractor, it's a relatively expensive construction. But I think it shows it. It's a high quality construction of the sort you can't get anywhere else.
We've built a chalk wall where the entire building was curves. Some of them were simple curves and some of them were compound curves. And we charged at that point, it was a few years ago now, £160 a square metre. After the job was finished, the surveyor, who we've done quite a lot of work with subsequently, admitted that they were very interested in rammed chalk because the equivalent brick cost would be £500 a square metre in curves. So we know that we can, metre for metre in curved work, we can absolutely do it a lot cheaper. When you get into something like this, where it's straighter line stuff, then the competition gets a little bit different. It's very easy to say, well, we know that we can put in lightweight concrete blocks for £40 a square metre. Yeah, but do you really want to look at them? Now you've got to put some plaster on, now you've got to paint over the top, etc. and so on. And then you get into this whole question about maintenance. That we're into a building industry which is maintenance free. But of course that's a load of nonsense. Everyone paints their walls again, and that is maintenance. So all of these issues, it kind of depends where you stand as to how they end up.
All the schemes featured in this programme clearly are funded by clients with a sustainable agenda. But what are the chances of unstabilised rammed earth entering the mainstream construction industry?
Making rammed earth more mainstream requires a whole series of different actions. Everything from teaching architecture students to working with contractors. Legislation might help at a certain level. We're doing a lot of work with standards in Africa, in Europe. At the moment we are in a situation where concrete has standards associated with it, and so people can use it without incurring more insurance issues, and we don't have the equivalent with earth. It's not a level playing field, it's something that we have to work to even out.
I'm not saying it's going to become a common everyday material, but for a building, a lecture theatre, which is a special place, I think a special material is quite perfectly feasible. And places like theatres and public spaces, you want something a bit better than the average. And I think that's what you're getting with rammed earth.
A lot of the time I'll go into an architect's office and people will say, why should I do this? And 10 years ago I would say, well, there's this thing called climate change. And quite often you'd get a bit of a blank look. Now that's not the issue. Everybody knows what climate change is, and they're beginning to understand how much CO2 comes from the production of cement. But it hasn't yet fed into a culture of building low buildings with low emissions. At the moment, I still am put on the spot to say why we should do it like this. I'd like to put it the other way and say, actually, why are you making a low building out of concrete? Why are you making a low building out of material that you can build the Twin Towers from? You wouldn't build a Ford out of titanium. Why are you building a low building out of concrete?